Hello everyone, welcome back. Today we are diving into a brand new update on the third known interstellar visitor, 3I Atlas. Over the past few weeks, something interesting has been happening. Multiple rotation periods were reported. The jets appeared to wobble. For a moment, the physics did not quite line up. But now, a new analysis may have just explained the wobble, and it significantly changes how we understand this object. Let us break it down. Zooming in on the inner coma of 3I Atlas, the Hubble Space Telescope reveals something remarkable. Instead of a chaotic spray, three distinct dust jets leap out from the glare, each one separated by about 120 degrees, forming a near-perfect triangle around the nucleus. These jets do not just point outward and freeze in place. Over hours, their directions swing gently back and forth, tracing arcs about 12 to 13 degrees wide. To make these features stand out, astronomers used a clever image processing trick called the Larson Sekanina filter. By subtracting away the smooth radial glow of the coma, this method sharpens the view and lets the jet structure pop against the background. What is left is a crisp, almost geometric pattern, three luminous spokes equally spaced, each showing a subtle but measurable sway. This is not the signature of a random tumbling body. It is a display of order and regularity, as if the comet's nucleus is spinning with purpose. The imaging team behind these results captured not just static snapshots, but a living, breathing rotation, one that hints at a deeper story waiting to be decoded. Confusion sets in the moment astronomers try to pin down how fast 3I Atlas is spinning. The jets in the images look orderly, but the numbers behind them tell a messier story. When analysts plot the position angles of the jets over time, three different periods jump out, one at about 2.9 hours, another around 4.3 hours, and a longer one near 7 hours. It is as if the comet is keeping three separate clocks at once. To make sense of this, they turn to a Lomb Scargle periodogram, a tool built for teasing out cycles in unevenly sampled data. The result is three sharp peaks, each with a false alarm probability well under 1%. That means these signals are real, not just statistical noise. But how can one nucleus have three rhythms? The puzzle deepens when they fold the photometry, the brightness variations, on the 7-hour period. The light curve lines up smoothly, as if the comet prefers this rhythm. Meanwhile, the position angle data, plotted with error bars, shows a clean sine-like wave with an amplitude of about 12 to 13 degrees, yet those shorter periods refuse to disappear. Monte Carlo simulations of the residuals confirm that this is not just a fluke of the data. All the evidence points to a real physical mystery. The jets behave with geometric precision, but the timing signals seem to clash. The team is left searching for a unifying explanation, one that can reconcile the elegant order seen in the images with the tangled web of periodicities revealed in the numbers. One rotation, three active vents, and suddenly the math gets interesting. Think of a lighthouse with three beams instead of one. As the lighthouse spins, each beam sweeps past your line of sight at regular intervals. If you watch from a distance, you do not just see the main rotation, you see flashes each time any of the beams points your way. That is what happens with 3I Atlas. The nucleus spins around one time every 7 hours, but with three fixed jets spaced 120 degrees apart. Each jet comes into view in turn. This creates extra signals called harmonics at roughly 1/3 and 2/3 of the main period. The exact timing shifts depending on your viewing angle, but the root cause is simple geometry. What looks like three separate rhythms is just the echo of one spin multiplied by 3.
Picture the nucleus of 3I Atlas as a spinning top.
But with a twist, its jets are not all the same. One vent sits close to the rotation pole, pointing almost directly away from the sun. This polar jet hardly moves at all as the nucleus turns, so its position angle stays nearly constant, barely shifting by a few degrees. In contrast, the other two vents are set closer to the equator. As the comet rotates, these jets sweep out much larger arcs, swinging back and forth by about 12 to 13 degrees. The difference is all about geometry. When a jet is aligned with the spin pole, there is little change from our viewpoint, but for jets farther from the pole, every turn of the nucleus makes their direction on the sky swing wide. This simple arrangement, one steady anti-sunward jet and two swinging lower latitude jets, naturally explains why the signals look so organized and why the apparent wobble is strongest where the jets are farthest from the pole. Stable rotation is not just a curiosity, it is a clue about what is happening inside 3I Atlas. When jets burst from fixed locations, they act like little thrusters, pushing and pulling on the nucleus with every outgassing event. Over time, these forces can change how fast the comet spins or even shift its axis. But the fact that we see such regular geometric motion tells us the nucleus is still holding together as a solid, coherent object, not breaking apart, not tumbling, but spinning smoothly through space. As 3I Atlas moves away from the sun and its activity fades, those jets will weaken, and any tiny imbalances in thrust could start to nudge the rotation period. That is why astronomers will keep watching, tracking for subtle changes, maybe a slow drift in the spin rate or a tilt in the axis. Each new observation offers a chance to catch the moment when internal forces finally start to win out over the comet's own stubborn stability. The story is not over, it is unfolding with every turn. Today, 3I Atlas reminds us that even interstellar mysteries can yield to careful observation and clear thinking. The universe still surprises us, but our tools for understanding it have never been stronger. Thanks for watching.